Welcome, everyone. In this session, we are going to explore how we can make sense of data by finding underlying mathematical relationships, a process central to scientific inquiry and data analysis. Specifically, we will focus on curve fitting, which is a powerful technique for fitting data points to scientific models or functions of a particular form. We will be using a Python package called SciPy, and within it, a very useful function called curve_fit from the scipy.optimize module. Our main learning objective is to understand what curve fitting means, how to perform it using Python, and how to interpret the results, including the parameters of our fitted model and their associated uncertainties. We will see that curve fitting involves collecting data, selecting an appropriate mathematical model, estimating the model's parameters to minimize the difference between predicted and observed values, and then evaluating how well our model fits. By the end of this lesson, you will be equipped to take a set of experimental data, fit it to a chosen function, and extract meaningful insights from this process. A skill widely applicable in various fields for making predictions and understanding complex systems. We will now put these ideas into practice with an exercise. Imagine you have a dataset consisting of x and y values, and your goal is to determine if a quadratic relationship, specifically a function of the form y equals a times x squared plus b times x plus c, can describe this data. The first code block sets up this problem. It imports the necessary libraries, NumPy for numerical operations and Matplotlib for plotting. It then defines our sample x and y data points as Python lists, which are subsequently converted to NumPy arrays for efficient computation. A crucial step is defining our model, which is a Python function named f. This function takes x and three parameters, param_a, param_b, and param_c, and returns the value of the quadratic equation. To get an initial feel, the code assigns some trial values to a, b, and c, and then creates a scatter plot of our actual data points alongside a line plot of our quadratic function using these trial parameters. This initial plot helps us visualize how far our guess is from the actual data, setting the stage for the optimization process where we will find the best possible values for a, b, and c. Now that we have our data and our model function defined, the next step is to actually perform the curve fitting. The code block you see uses the curve_fit function from the scipy.optimize module. We provide three essential arguments to this function. First, our model function f that we want to fit. Second, our independent data xdata. And third, our dependent data idata. The curve_fit function then works its magic and returns an object, which we have called results. This results object contains two main components. The first component, which we can access as results at index 0, is an array holding the best fit values for our parameters a, b, and c. These are the values that minimize the difference between our quadratic model and the observed A data. The second component, results at index 1, is a more complex structure called the covariance matrix. This matrix is incredibly important because it tells us about the uncertainties and correlations of our fitted parameters. Specifically, the diagonal elements of this covariance matrix represent the variance of each parameter. By taking the square root of these variances, we can obtain the standard error for each parameter, giving us a measure of how precisely we have determined a, b, and c. Having obtained the results from curve_fit, our next task is to extract the useful information and visualize how well our model fits the data. This code block accomplishes just that. First, it retrieves the best fit values for our parameters a, b, and c from the results object, specifically from results at index 0. It then prepares a plot. On this plot, our original x data and y data are displayed as distinct points. To show the fitted curve smoothly, it generates a new, denser set of x values called xp. Using these xp's values and our best fit parameters a, b, and c, it calculates the corresponding y values from our quadratic function and plots this as a red dashed line. A legend is added to clearly distinguish the data points from the fitted curve. Critically, the code also calculates the standard error for each parameter. This is done by accessing the diagonal elements of the covariance matrix, which is results, at index 1, and taking their square root. Finally, it prints out the best fit values for A, B, and C, each accompanied by its calculated standard error. This provides a complete summary of our fitting procedure, both visually and numerically. This next exercise demonstrates a key application of a fitted model: its ability to make predictions or to be evaluated on new data. Here, we want to see how our previously determined quadratic function, with its best fit parameters for A, B, and C, behaves with a completely different set of x values. The code begins by defining a new array of x coordinates, x data 2. It then uses our fitted function f, along with the optimal ABF, BBF, and CBF values we found earlier, to calculate the corresponding y values for this x data 2. To visualize this, the code creates a plot that includes several elements. The original data points from xdata and xdata are shown. The new points based on xdata 2 feet and its calculated y values are also plotted, perhaps with a different marker. Finally, to show the overall behavior of our fitted quadratic model, it creates a combined and sorted array of all x values from both datasets and plots, the function f, over this extended range. This visual comparison helps us assess how well our model generalizes beyond the initial data used for fitting, which is an important test of a model's utility. Let us now apply our curve fitting skills to a classic physics problem: determining the acceleration due to gravity, which we call g, by analyzing data from a ball dropped in a vacuum. We are given experimental data, a set of vertical distances the ball traversed, and the corresponding time intervals it took to cover those distances. Our objective is to use this data to calculate the best estimate for GAG, and also to determine the uncertainty, or error, in this calculated value. Physics tells us the relationship between time t, height h, and g. We can express this in two common ways. Either time t equals the square root of the quantity 2 times h divided by g, or height h equals 1/2 times g times t squared. For this example, we will use the first formula involving time. The provided code block starts by importing the necessary libraries, including NumPy and SciPy's optimization tools. It then stores the given experimental height data into an array called HData, and the time data into an array called AData. Crucially, it defines a Python function named t, which takes height h and the gravitational constant g as inputs, and returns the calculated time based on our chosen physical formula. This function t will be our model for the curve fitting process. Before we perform the actual fit to find the best GAG, the first code segment here helps us visualize the situation. It takes our experimental height and time data points and creates a scatter plot. Then, just for comparison, it plots a theoretical curve using our physics model, t equals the square root of 2 h's over g, but with an assumed or arbitrary value for g, such as the standard 9.81 meters per second squared. This allows us to see if our data roughly follows the expected trend. The second, more important code block then uses scipy.optimize.curve_fit to find the optimal value of g. It passes our model function t, the h data, as the independent variable, and t data as the dependent variable. From the results returned by curve_fit, it extracts the best fit value for g, which it calls gbest. It also extracts the variance of this estimate from the covariance matrix, and then calculates the standard error by taking the square root of the variance. Finally, this code prints the best fit GI value and its standard error. It also generates a plot showing the original data points along with the curve predicted by our model using this newly determined GI best, providing a clear visual assessment of the fit. Up to this point, the standard error calculated for our best fit parameter, like HAG, has been based solely on how spread out our data points are around the fitted curve. However, in many real-world experiments, our measurements themselves have inherent uncertainties. For instance, when measuring the time it takes for the ball to fall, there might be an experimental error, perhaps plus or minus 0.1 seconds for each measurement. The ziacp.optimize.curve_fits function allows us to incorporate such known measurement errors into the fitting process. We can do this by providing an array of these errors, corresponding to each seed data point, to the sigma argument. We also set the absolute_sigma argument to true, which tells curve_fit to treat these sigma values as the actual standard deviations of our GUI data. The code demonstrates this by first creating an array, error_in_t, where each element represents the uncertainty in the corresponding time measurement. Then, curve_fit is called with these additional sigma and absolute_sigma arguments. As a result, the calculated best fit value for DAG and its standard error will now account for these measurement uncertainties, generally leading to a more realistic and often larger standard error for DAG. The plot also visually reflects this by showing error bars on our data points. Throughout this lesson, we have delved into the essential technique of curve fitting, learning how to uncover mathematical relationships hidden within data. We focused on using the curve_fit function from the SciPy library, a powerful tool for this purpose. You have seen how to define a model function, whether it is a polynomial or a physics-based equation, and then use curve_fit with your experimental data to find the optimal parameters that best describe that data. A critical aspect we explored is understanding the uncertainty associated with these parameters by interpreting the covariance matrix to calculate standard errors. Furthermore, we learned how to incorporate known measurement errors directly into the fitting process, allowing for even more accurate and realistic assessments of our model parameters. This entire process, from choosing a model to evaluating the fit and its uncertainties, is fundamental for analyzing experimental results, building predictive models, and gaining deeper insights from observations across many scientific and engineering fields. Reflect on how these steps combine to transform raw data into meaningful knowledge.